Now if we want to further analyze this rectifier, one of the analysis would be to harmonic analysis of the output voltage. So I have the FFT analysis. Okay, so we need a signal. We need a signal to be analyzed, to analyze its FFT, and for that, let me just get rid of the input voltage for the moment. I'm interested in the output voltage, so I'll just come here to the settings, to the logging, and log data to the workspace, and I'll choose structure with time. The reason I'm doing this is if you observe this FFT analysis here, the demand is structure with time. So this is the reason I'm choosing the structure with time for logging, and now I'm going to run it again so that we can log that data, and once it is done, we have this kind of simulation output. If you double click it, you'll find the scope data, which is actually, if we recall it, scope data, structure with time, this is our required data. So I'll just type in P equals out, which is this one, dot scope data. Alright, so P is the thing that we need for FFT analysis. So I'll just double click tools, FFT analysis, and here now you can see that it automatically detects P, and here is the waveform, the output voltage waveform of the half wave rectifier. So here we can set up things regarding the input signal. We can select the FFT window, that's just the one cycle, and we can, if there are multiple signals, we can select out of those many. Similarly, here are the options regarding FFT. So the start time and the number of cycles, we can also set this to 2. So here you can see that the number of cycles are now 2. And the fundamental frequency, that's important. We have a fundamental frequency of 50, and then we have maximum frequency. That means how long we want to, how many harmonics we want. So we can, if we want many, we can go for 2000, and if we want fewer, we can set it to 1000. Similarly, which kind of magnitude, means a spectrum we are looking for a bar graph, or just list the magnitude of the harmonics. Okay, so frequency axis in hertz are harmonic number. If we set it to hertz, it will be like 50 and multiples of 50, and if we set it to harmonic order, it will be like 1, 2, 3, 4, and so on. So let's set it to hertz. Once done, we can press the compute FFT, and there we get the FFT of this particular signal. It is important to mention here that the magnitude is with respect to the fundamental, which means that the fundamental the whole spectrum is scaled with respect to fundamental, which means the fundamental gets to 100 and the others are relative to the fundamental. Since we are dealing with the rectifiers, we would like to have relative to the DC component. Okay, so when we are plotting this FFT with respect to the DC component, that means the DC component will hit the 100 and the others will be relatively scaled. So the shape actually preserves, but the normalization, in fact, is we can set that to DC, we can set that to the fundamental, we can set that to a specified base. So if we are not interested in normalization, we can just do it directly. Okay, so okay, once we are done, we can use this FFT for any report. We can just save this FFT graph. We can just name it FFT of half-wave rectifier. Similarly, we can save this guy as well as the output of half-wave rectifier. You can just press this and save as. We can also just copy and paste if we want. Okay, so with that we learned how to find the FFT, the steps to find the FFT of a signal in the sim power system. In the Simulink, we just learned.